So, where to begin? Curves. You study curves, you study graphs at school, and you're going to hear lots of talk about functions. Now, functions are not always curves, but very often they are, let's say. And you're going to hear this word, functions of this, functions of x and y, and when this is a function of time and but now it's a function of position and function and the derivative of the function, and it's going to drive you quite crazy. And this is the first thing I just want to talk about before I get into my shit on curves, is that functions are answers to questions. When we say something's a function of t, a time, function of t, or a function of position, position in space, three-dimensional space, it means the answer is to a question about what will be happening at this time or at this position. The answer relates to it. Okay. So functions is a fancy way to say we're asking a question and we're getting answers. This is why functions, when they're graphs, they have to be give a single answer. For example, this is a function because everywhere on the graph you get a single answer. This is not a function because the answer and this is the question line, okay, and this is the answer line, y, and we get two answers. So therefore, this isn't what we call a function. It is a curve, and we can study it mathematically, just as the circle is a curve, and the ellipse that we study mathematically, and all very interesting and very good. But I just wanted to clear that up about functions. Right, so I'll keep it on this. I almost started to do what you probably know as the sine wave in this is a function, and the cos wave, which is essentially the same thing, only shifted. So there's a thing you miss in mathematics high school about importance of translations. This is a translation. Okay, so you learn this abstractly in maths, and it's like, what the hell's the use? It did occur to me a day or two ago. There's another key thing that translations that we missed the applicability of it. But it'll come to me. It may well have been this. Right, so you study the parabola this way, which is a quadratic function, and it always has an x squared function, and you learn to draw these graphs and learn to draw it plus 2x plus 5 with a constant y equals. This is the function of x, because y is equal to a function of x, because the questions are about the x value, and the answers we get are y values. Okay. Parabolas, you learn about exponential graphs, and they tell you, oh, these are really important graphs for nature, and what other graphs? Oh, you in basic high school you'll study this straight line graph and all these variations, and you learn how to plot them, and you don't learn what it really means to be in love with functions and in love with curves, and why you ought to be. Take for example a question of sliding a ball down to a position x of a cliff. You know, clearly the shortest distance between a path between any 2 points is a straight line. Is it the shortest? Is it the quickest way though? If we're to make a slide that gets us the quickest, or maybe we want to drop it really steeply and get some velocity in there. Maybe, and how would this be described? Would this be, you know, a reciprocal function? Would this be a quadratic function? Some sort of quadratic part of a curve? What would minimize the amount of time? Now, this is a calculus problem, calculus of variations, which I've not studied much on, but this is where this is an avenue I need to progress along, and it's very interesting. Solving for the minimum, yeah, solving for the minimum. Now that's kind of, and it turns out, so I'm led to believe, is that, and this is kind of neat, that the type of curve, which I don't know if this will work, but is one of these. Whoa, it's not worked. Yeah, but it's a cycloid. It's a cycloid, as though this is the kind of curve that, as if you're rolling a wheel. Well, this is the solution to this problem. What the diameter of that curve is, I don't know how to calculate, but that is really interesting. And it turns out that no matter where you put the ball, it actually takes this. It's also a same time. Supposedly, that will be t, that will be t, and it's the same time. That will take the same amount of time. Well, that's really funky, that. Another. This was supposedly a problem for a long while, about suspending a chain or rope between 2 points. This turned out to be a minimizing of the stress sort of energy, I think, in the string. And for lots of people used to think it was a parabola, but it's not the parabola. It's the catenary, which is a hyperbolic, is it? Function, the cosh hyperbolic function, hyperbolic cosine function. And this is a calculus of variations problems, which is an applied maths course, which I know they do it at master's level, I think, on Open University. I would like to take it, but it's another minimizing problem, which relating to physics is, you know, it's really interesting. The whole concept of the principle of least time, and a light ray will travel through a block such that it's the minimum amount of time that is. But how does it know when it just turns this angle? How does it know that this way was shorter than that way? And there's this whole business about perspective, some ways of looking at laws, comes to issue here. I mean, you have to know that it probably gets raised. in high school, you know, that's the parabola shape, the fundamental shape of the parabola is also the fundamental shape of a projectile. Okay, and that it doesn't strike you, but roots in dynamics and algebra, but the roots become important because we can solve for these points, which turned out to be quite important because these are the start points and the finish points in a projectile situation, and that's interesting. Curves, and it was only some time ago. I never studied it, but conics. I mean, so you know about the circle. You know about the circle. Let me here's my other device. Okay. So I made this to. If we was to play a game, and you was to guess. You had to choose a time when you had to say when this endpoint was going to stop, and when you could say what I'm trying to say is we're going to make a mark. Okay, you're going to choose a position on this travel, and you're going to make a mark, and that mark you choose, you have to say stop when it's at that mark, right? And you have to ask yourself, what would be the position you would choose to make the mark when this is travelling? Okay. Now, hopefully, you would see that at this point, it's kind of going at a maximum speed. If you chose to make your mark here, then you're most likely to say stop and overshoot, because it's passing. At this point, it's actually instantaneously stopped at one point. You know, it goes from going in the forward direction to the backward direction. And many machines I've worked with use this as a simplistic form of speed control. You know, it makes a nice, you know, a carriage can move into one machine, and a rather simplistic braking system can essentially, with very little error, stop the carriage in, and then something happens, it places something on the carriage, and then it moves it out, blah 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 blah. This reciprocal action, I've come across it in a lot of machines, but this motion is a sine wave. If you have the same circle, and if it's a unit circle, if at regular intervals of time you plot this height, you divide time up like this, say, I don't know, for whatever speed it's going, 10 seconds, 5 seconds, and you say in 10 seconds you'll make sure this is done one revolution. Okay, then clearly, and you measure off the height. The height corresponds to a speed, and the speed will be plotted like this, reaching a maximum height after a maximum height travel in this direction at 2.5 seconds, yeah, or 90 degrees. So, or pi over 2 radians. Okay, and what's happening? Take that angle projection at the right time, and at the next angle at the next time. Okay, if this was 1 meter, and I've done this just to show my sister who teaches maths. If you make this 1 meter and then measure this out, turns out these lengths, you've actually made yourself a calculator, and if you measure these lengths, that will be, and it was whatever 0.618 at that point or something, that will be centimeters long. And if you put in that angle into your calculator, you'll get the sine wave point, the sine of that angle as blah 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 blah. But so you've seen that the reciprocal machine functioning, but this same motion comes from a spring bouncing up and down. You know, it comes down to a maximum velocity, to a minimum velocity, and bounce, and at midpoint it's going to be at a maximum velocity up in that direction, right up to a 0 point, and then it changes direction, and then it'll be in a maximum direction. And it's the same sine wave. This sine wave, essentially cosine wave, and circles, appears in all kinds of mathematical situations, and is just embodied in the almost all physics. You know, it's like the circle just has this really deep meaning in reality. I mean, but in my opinion, you ought to know, I mean, it's an approximation. It's because there's no real numbers, and many of these values that turn are irrational, and they have no physical reality in one sense. So this is some kind of mathematical representation, which is really interesting, I think. And relatively late in my career, as I didn't understand that this is that so many of these curves were had the geometrical connections. You know, you got the circle of the conic. Now I forget. I think that's the ellipse. The ellipse being a section through a conic. Now, one is, no, I forget. One of these is a parabola, and one is the hyperbola. I think that looks like the hyperbola. I'm not sure. And that looks very much definitely like the parabola, doesn't it? But it's and I've not studied these in great detail, but it's to do with the angle of whether it's been in parallel or not. But I find this stuff really interesting and very beautiful, as that is the word. It's surprising and whatnot. Was there anything else to say on curves? So you've got all these curves, you know. I mean, so then you've got statistical curves, to, you know, standard deviations, what it means, you know, to have a tight curve. What if, and the importance of questions, as to if you say you had a maths teacher whose exam results look like this, versus a maths teacher whose exam results like this, what kind of story explanation could you give? Who would be the better? I mean, this maths teacher, it could be failing at 35%, but it means something, or another maths teacher who passes everybody at 55%. But then another maths teacher, he might have this central point, you know, of 45%, but some people you know, are getting 90%, but a great many are failing, perhaps. What story can we tell that would account for that? Any other curves that Oh yeah. So this is just curves. I mean, you've got to study your curves, man. You've got to understand your functions. But oh, is that me done? Oh. No, I hasn't done so much. But you got to take your curves. Then, I mean, Einstein has brought an interpretation to gravity as deviations in what can be thought of as a surface, you know, and that orbits that are ellipses as well, you know, like the mathematical curve, you know, that we have ellipses are in surfaces. You've got to understand then, you know, to understand general relativity, I believe you've got to really and this is something I'm weak on, the idea of what straight lines then become geodesics, which are not which are great circles on a sphere, and topology then becomes important. Okay, so you have the whole topology thing and the idea of toruses, you know, donuts is a topological surface and concept. You know, you've got you know, all vortex curves. What kind of curves are those in surfaces? Which leads to essentially higher calculus as well. It was when in calculus of multivariable calculus and vector calculus is learning then not to just differentiate this single and find and consider gradients, because when we analyze all these curves that we've talked about, we're always, by nature, we measure gradients of things, you know. The answers we're always finding are gradients usually. When we measure somebody's velocity, for example, you've measured a speed, which is a rate of change, which is a gradient, and we're always asking what possibly could be the function that the gradient function belongs to. And this is although the answer is given as a derivative and a gradient, we're interested in what the real story, that predictive story, is about. Is about the thing that gives rise to the gradient. So at higher calculus, we're taking this deeper with multivariable calculus, which is considering position vectors on surfaces and tangent planes, and this is all gets really interesting. This is where I need to take my mathematical development. I recently realised. So you're having to invoke matrices to understand all these concepts, and I want to understand general relativity, and I believe I need to get to know what a tensor is, and I've recently made some ground on understanding that, being that that when we ascribe numbers and concepts to all these with multiple numbers groupings, it turns out that as an example, we want to ascribe want to hang a number or an object associated with something in nature, and that if you consider how some stresses might be flowing through a material, that at some point you can consider that it has a direction, and the surface, a particular value of stress, has has some direction about it, and it has a normal to it, and this is only representable. I mean, plain high school physics of stress, just, you know, stress on a rod, you just consider everything as being straight lines, and so it just has one number attributed to it. But stresses on a material from complex directions, you can give rise to really one numbers to consider what's going on now in this material. One number no longer is any use to describe stress in the material, and so the tensor is essentially a matrix, an array of numbers, which is in a sense embodying this whole holistic concept that there's a unit of direction and a surface direction. So there's not only a direction of the stress, but a kind of a direction of the surface pointer as well. And this concept can be expanded to bigger and bigger details, and the fact that your mind might encompass this higher physics, there's no reason, just for what the mind can visualize, for the principles of attaching numbers and arrays of numbers to real things in reality, and expanding these arrays gets larger, and that seems to be what's going on with general relativity. Those more surfaces that I like to draw than this, but I'm sure. Yeah, but I mean, you know the deal. But you know, all these curves can be considered, and this is how you have to learn your tools. Can be considered as rotating, and if you like, generating a surface, and then you get this becomes in a 3D plane. This also becomes a functional surface in terms of it has definite values, positions. Listening to Leonard Susskind on the Higgs boson was really interesting. How he talks about the potential, the Mexican hat function, which is I've screwed that totally. I mean, how do you draw a Mexican hat function? Which is essentially the physics of a Mexican hat function. Is an account for a field, and you may or may not, but fields are representations where a surface can be a plane of a constant value in a field. Oh my God. 28 minutes of rambling about surfaces, but somebody might like this. Oh yeah, I forgot, but then the great connection between sine waves and the exponential is just awesome. When you get the Euler function, the Euler relation, e to the I pi plus 1 equals 0. I mean, that's just phenomenal. and this comes about because of that relation. And what's that equal to? What's equal to z? It's just the number, which is just the number on a circle. So that's a complex number on the plane designating the point, which designates sort of, which allows you to see the connection between a circle, complex numbers, a circle, and a sine wave. But if it turns out that I can't remember it now. E has an expansion. Let's call it A1 plus B1 plus I can't remember the expansion I ought to do. I know it's like over factorial business, but sorry, A2 plus B2 plus A3, etc. Now the cos expansions, for example, I might have the order, but essentially it's like odd and even terms, yeah? Yeah. Cos expansion is all the A terms, and the sine wave is all the B terms. You plug pi into this, ipi, sorry, and out pops this beauty. Right, that's enough. That's enough rambling for now.